Okay, I'm recording now. I'd like to thank very much Professor Frank Tipler for joining us to answer a few questions about his work. Also with us is Micah Redding, who interviewed Professor Tipler for the Christian Transhumanist podcast a few weeks ago. Now, Micah's interview was most focused on theology. Our interview now is going to be more focused on science and the fundamental physics on which Frank Tipler's work is based, but we're going also to come back to theology at the end. For who is not familiar with the work of Professor Tipler, but I guess most people viewing this are, the three books are here on the screen. The first was called The Anthropic Cosmological Principle. The second was called The Physics of Immortality. And the third is called The Physics of Christianity. In fact, I'd like to start with a few questions about the book. And reading the reviews, especially the reviews written by physicists, I noticed that basically everyone loved the first book. The reactions to the second book were kind of mixed. Some people liked it, some people didn't like it so much, and some people didn't like it at all. And I'm sorry to see that most of the physicists who wrote reviews about the third book, Physics of Christianity, didn't like the book at all and found a lot of things to complain about. Now, Frank, why do you think it's like that?
Well, I think it's somewhat ironic that things went more or less like that. I think, however, that there was much more hostility to the Anthropic Principle book, which I wrote with John Barrow, than you recall. I had some very good reviews, but also some very critical reviews. What I think has happened over those three books is that I am systematically becoming more and more rigorous in my physics, that things I would have to assume in earlier books I would then prove given the laws of physics, which is why I find it truly remarkable that the most rigorous in physics book of all, the Physics of Christianity, is the one which physicists most criticize. I put it down to the fact that in the Physics of Christianity, I assume that the general relativity in its quantized version plus the standard model is a theory of everything. Most physicists do not like this idea. They think they would like to discover some new physics. If I'm right, on the other hand, there's no new physics out there for them to discover. Their careers would be at an end. In that sense, I'm a real threat to them professionally. This is what I would suggest to be the really underlying reason for the hostility. I use nothing in the Physics of Christianity but standard physics, general relativity, quantum mechanics, and the standard model of particle physics.
I see, and in fact, we will be coming back to these points later on. But don't you think that another reason for the hostility the physics of Christianity could be the fact that many scientists just hate the idea of taking religion seriously in a scientific context?
I think you are, of course, right. I just wanted to point out the reason entirely inside of physics why they might be hostile to it. But I think, indeed, a major reason would be that scientists in general think religion is just nonsense, and anything that is intended to justify religion is therefore also nonsense. Now, I think that's completely inconsistent with the laws of physics, because I see no reason why, if the universe is deterministic and I have written a series of papers in which I prove that it most certainly is. Einstein got it right. God does not play dice with the universe, and Einstein was a theist like myself, so he meant God rather than just nature. And if God is control of everything, and remember my position, God is the cosmological singularity, then the singularity controls everything. So it's quite plausible that he would have revealed himself through human prophets thousands of years ago. And most of the things that are discussed in the physics of Christianity, like a triune God, are also present in the other human religions on this planet, the exception, of course, being Islam.
Yes, thanks. As a matter of fact, yes, it's easy to have the impression that most physicists hate religion, but as a matter of fact, if you do some digging around, doubt that many well-known and very distinguished physicists actually do have religious ideas. On the other hand, for a young physicist who is just starting his career, don't you think that perhaps acknowledging any kind of religious belief would be not very advisable for those young folks who wants to advance their career in physics?
I think once again you are right. And I think it even affects senior people. Let me use two examples of friends of mine who I know are true believers in Christianity, John Barra and Martin Rees. I know them well enough to know perfectly well they are Christians, but you would never know it from their actual work. They never write defenses of Christianity. I think that even in their incredibly senior positions, Martin Rees, for example, is currently the Astronomer Royal of England, and he's just retired from the position of President of the Royal Society. If a scientist of that rank is afraid to acknowledge that he is a Christian, what could a junior person possibly expect? Certainly ferocious retaliation. Now, of course, I've got relatively minor retaliation here at Tulane, but only because I am a tenured professor. But I still have gotten no raises in about 10 years, precisely because of my defense of the truth of revealed religion.
Interesting. Let's come to another point. Yes. By the way, you see that the text of the questions is on a screen. I made that especially for the recording, so you can also read from the screen. Now, I am curious about what were the changes in your thinking between the first and the second book, between the second and the third book, and after the third book.
Widen my screen so that I can see this. I can still see only part of it. Let me try to widen my screen further. Ah!
You're not holding.
I forgot to push down the button. I got it now. What happened is that I had the idea of the final singularity being God at the time I wrote with Barrow the Anthropic Principle book. But and I wanted to discuss the connection with religion in some detail. But my co-author was rather frightened of that. I mentioned that he does not want to reveal himself as a Christian. So we compromised, and I mentioned there might be some religion here only in a footnote at the last chapter when I was discussing the fact that if life goes on forever, then the final singularity has to be a single point in the Penrose C-boundary topology. In my second book, I decided to follow that through in gory detail, and I was thinking about how far the central claims of religion could be incorporated into the physical theory, and it was as a consequence of my interaction with the great, late, unfortunately, theologian Wolfhart Pannenberg that I realized there was a resurrection theory in there, which just came so naturally out of the physics. So I had a large discussion of that in my Physics of Immortality book. Now, one of the criticisms that had been made by theologians, I remember very specifically, well, if the final singularity is the God, what about the initial singularity? It's just as singular as the final singularity. And I started thinking about that. And obviously, if
I think I have lost your voice for a few seconds. I'm not hearing you now.
can you hear me now?
Yes, I can.
Yes, I can. Okay, maybe I was not holding down the control key sufficiently hard. The point was that I realized that I had a third singularity in my drawings representing the many worlds picture in the Physics of Immortality. There actually was a singularity which connected the final singularity with the initial singularity, and you could see all these singularities, therefore, were really one. So you have three singularities, which are really the same singularity, but are nevertheless distinct. Obviously, that suggests immediately a trinity, certainly if you've identified one of the singularities with God. Then, looking in more detail, I found out that it is natural to identify the final singularity with God the Father, because in the passage, Exodus 3:14, Moses asks God for his name, and God replies, Ehya Asher Ehya, which in Hebrew means, I will be what I will be. Aha! Ultimate future. And then, what about the initial singularity? Well, if you look at the beginning of time as pictured in Genesis chapter 1, verse 2, you have a phrase, the Spirit of God hovered over the waters. Now, Rauch Elohim is the Hebrew Spirit of God, and the great Christian theologian St. Augustine said, this is indeed a reference to God the Holy Spirit. So I've got natural identifications from the leading theologians about which God is which, and there's only the third singularity to identify, and so I identified the third singularity with God the Son. That's how the theology is falling out from the physics.
In fact, this is the content of the Physics of Christianity. And did you have any other new idea since 2007 which can extend that?
What I'm now planning is a third book. Well, if I've written a book on God the Father, which was the essential content of the Physics of Immortality, and I've written a book on God the Son, which is the central content of the Physics of Christianity. Well, I need a third book on God the Holy Spirit, and this is what I am now working on. What I'm trying to do theologically is show how Genesis chapter 1 is a nice picture of how the universe actually began. And let me just give you a little preview of two interesting verses. Everyone is aware that and God said, let there be light, and there was light. This has always been interpreted as light being the first thing ever created, and many cosmologists before me have noticed this very interesting parallel between Genesis first chapter and modern cosmology. There is another very interesting one. There is the phrase immediately after the creation of light, God said, let there be a firmament in the midst of the heavens. Now, the Hebrew word which is translated in the King James Bible, firmament, actually has a somewhat different meaning. It means expansion. Now, as a cosmologist, I like that idea, expansion of the universe. It's there. In fact, the universe is expanding. We know that. And if you go to the original Hebrew, lo and behold, it is there in the original Hebrew. Now, you can expand on that in more detail. I'm not going to continue with that. That would be the content of my book, which I'm working on now. I am also concentrating most of my time on cosmology and seeing how we can prove that this theory that the universe is controlled by a theory of everything, which is just quantized general relativity combined with the standard model of particle physics. And I'm trying to use this time to go through the calculations and try to resolve as many cosmological problems as I can. Now, I've already mentioned that having a wave function which is concentrated on the initial singularity entirely, which means that the entire multiverse, not just our universe, but the entire multiverse springs out of the initial singularity, that automatically Sorry about that. My computer just shut down. I hope you can still hear me.
I can still hear you.
Okay, good. That will automatically solve two things. It will solve the flatness problem, and then you go through additional calculations, namely use the Bekenstein bound, and that will automatically solve the horizon and the homogeneity problem. This is just quantum gravity, standard quantum gravity from the Wheeler-DeWitt equation that solves these cosmological problems. Now, I've already mentioned in my 2005 paper, which I briefly allude to in my 2007 book, The Physics of Christianity, that the initial state of the universe had to be very special, and I am proposing that it was just one part of the fields in the standard model, an SU2 left gauge field. If that's all there was in the very beginning, then you have automatically a solution to another fundamental problem of cosmology, namely, why are there more baryons than antibaryons? Or more generally, why is there only antimatter, only matter as far as we can tell, and very little antimatter? Having such an initial state is the natural way to get baryogenesis. Now, two other problems which have come to the notice of cosmology are the lithium problems. There's just too much lithium in the universe. And also the what's called the scalar spectral index deviates slightly, but two instruments have definitely observed it, so I think we have to accept that it does deviate from perfect flatness, what's the spectral index, which is what you would expect from perfect flatness.
I lost your voice.
Let me try again. Can you hear me now?
Yes,
Okay.
yes,
Yes.
Apparently, I have to release the control occasionally in order for the voice to still be on. Don't ask me why. Now we know. Okay, so that's what I've been working on most recently.
Thanks. And in fact,
Thanks.
you
And in
have
fact, you have
anticipated.
anticipated.
Okay, now take.
Okay, now take.
Now don't hold.
Now don't
Don't hold the control key. Okay. In fact, you have anticipated my next question, which was about if you are writing other books, and which is good. I definitely look forward to reading these, I believe, two different books. When, more or less, can we expect them?
Well, right now I have an experimental group. I'm not going to say who they are or where they're based, but they're based at major universities. It's a collaboration, which are actually doing observations right now to see if if the universe began in an SU2 left gauge field, there should be some remnant of that in the microwave background. And remarkably, instruments which have been built to investigate the properties of the microwave background can be shown to have been designed in such a way that they would automatically eliminate the signal we're looking for. So what we've done is redesign a piece of equipment which would allow us to see this signal if it's there. So right now I'm spending a lot of time looking at their data that they've been taking. We haven't completed the data yet, but we're taking data right now, and I think we will eventually see something. I don't know that, of course. You do not know what the result of an experiment will be until you complete the experiment, obviously. But there are other signals out there that suggest that this signal is there. In my 2005 paper, I predicted that the Sunyaev-Zeldovich effect would be a factor of 2 too low than standard theory predicted. This is one signal which you would expect, if my theory is correct, from the cosmic microwave background radiation. And it was sort of seen in the WMAP experiment, but the most recent experiment, the Planck experiment, a magnificent instrument, cost $1 billion, it ought to be magnificent, actually finally showed that the Sunyaev-Zeldovich was too weak by a factor of 2. This gives me confidence that what we were looking for we will eventually find.
Thank you very much. So that we'll definitely be waiting for results and for the new books. Now let's move to something about the physics of your idea. And well, this is something which I have found surprising when I first read it in the Physics of Christianity, and then again in much more detail in your 2005 paper, is that you are persuaded that the quantum version of general relativity developed by Richard Feynman and described in his lectures on gravitation, which is basically a quite conservative elaboration of Einstein's general relativity based on modern quantum field theory, is a viable theory of quantum gravity. I was surprised reading that because I had the impression that most other physicists consider it as, yes, something valid, but only in a weak field approximation, and something which will have to be replaced by other more accurate theories in the future. So could you elaborate on this point?
There are actually two theories out there for quantized gravity. The Feynman quantum gravity theory that you mentioned, what Feynman does is just this very straightforward quantization procedure. We all know from the properties of gravitational radiation, of classical gravity itself, that gravity is a spin-2 field. So what Feynman did was quantize a spin-2 field. It was an obvious thing to do. There was another approach which was taken at the suggestion of John Wheeler and worked on in detail by Bryce DeWitt. So the resulting equation is called the Wheeler-DeWitt equation, which is another way to quantize gravity. I think, but I have never proven this, so take this statement with a grain of salt, I think that with appropriate boundary conditions, the two theories are equivalent. The two theories, however, do not assert that they are valid only for weak fields. The Wheeler-DeWitt equation, as DeWitt realized when he first tried to find a cosmological solution, has a singularity in there, and a singularity has to be considered as a strong gravitational field. It's sort of hard to say infinity is not a strong power. So the equations themselves assert that they are valid for arbitrarily strong fields. Weak, strong makes no difference for them. And I'm just saying, let's believe the equations, guys. There are no experiments showing that the Feynman quantization theory or the Wheeler-DeWitt quantization theory is only valid for weak fields. Every experiment we've been done to date agrees with the solutions to these approaches. My colleagues, I agree with you, think that these theories, however, are valid only for weak fields. There are two reasons for this. I mentioned one. They don't want to have the glorious game, which we've been now playing for centuries, to end. Once we discover the ultimate theory, then there is no more physics to be done, no more fundamental physics. You'll then, from that point on, the rest of time, you'll just be doing calculations in the context of these true theories. I don't think they psychologically want that. Now, there is, however, a valid reason for considering quantum gravity as represented by Feynman quantization and DeWitt-Wheeler quantization to be only a temporary stage. Sorry, my computer shut down. Can you hear me again?
Yes, I can. Yes, I can.
Okay. And that is the fact that standard quantum field theory is singular. That is, it's not an ultimate valid theory. And so if it was the case that Feynman gravity, which is a standard quantum field theory, were subject to the same restrictions as standard quantum field theory, my colleagues would be right. But what I have argued is that their view that these quantum field theories are inconsistent, the versions they've discovered are inconsistent, but they've never combined the standard model quantum field theory with Wheeler-DeWitt quantum gravity. I'm arguing that standard quantum gravity can stabilize both the singularities in the infinities in standard quantum field theory and also eliminate similar singularities from the Wheeler-DeWitt equation. The only singularities you will have as a consequence of this theory with the correct boundary conditions, which have the singularities in them, are the singularities at the end of time. One way to think of this is that the singularities in quantum field theory, they don't call them singularities, they call them infinities. The infinities, there are two types, the ones that are renormalized away, and the type that arises from the fact that standard series expansion in powers of the coupling constants diverges It's only an asymptotic series, not a convergent series. I'm claiming with appropriate boundary conditions, those infinities are both of them, absorbed into the final singularity. But you cannot eliminate the singularity. My colleagues also do not like general relativity. They do not like standard quantum mechanics, quantum field theory, because they have singularities in them. The curvature singularity, which began space-time, they do not like that. They want to eliminate it. I think that that is a mathematical error, because we know that if you have what's called a holomorphic function, that's a holomorphic function is a complex valued function of a complex variable whose first derivative exists everywhere on its natural domain. Holomorphic functions, any holomorphic function which is not a constant necessarily has a singularity somewhere. That's just a fundamental principle of mathematics. Now, what I've been able to do in the past few months is I've discovered a relationship between the singularity that it has to exist mathematically for holomorphic functions, which are not constants, and the singularity which begins and ends spacetime. Ultimately, they're one and the same singularity, so you can no longer eliminate the singularity from quantum gravity than you can eliminate the singularity from non-constant holomorphic functions. It cannot be done mathematically. My colleagues are chasing a mare's nest when they are trying to do it.
Well, that's a lot of food for thought. Well, in fact, we will be coming back later. I am speaking. Are you hearing me?
I can hear you. I'm waiting for the next question.
Yes. Yeah, in fact, you kind of anticipated the next questions, which was whether the fact of putting together the standard model and quantized general relativity does actually constitute a theory of everything. And I think your answer was that yes, it does if you add the appropriate boundary conditions.
Correct.
And coming right to the next point, if you could, well, you have said all that already, but maybe just to keep in sync with the screen, summarize what you just said about what the right boundary conditions must be.
The correct boundary conditions are there cannot be any event horizons at any level of size. Not only can event horizons not exist around astrophysical black holes, they cannot appear in the microcosm. Now, what that means mathematically, no event horizons is mathematically equivalent to the statement that the final singularity is a single point in the Penrose C-boundary topology. And that, remember, is my fundamental starting point for my omega point theory, which says that the universe will end in a singularity which has no event horizons. What I've done in order to solve the problems of quantum field theory is impose the condition that event horizons do not exist at any level. Now, let me hasten to add that does not mean black holes do not exist. Astrophysical black holes certainly do exist. We've seen them. But mathematical black holes do not exist. Because what is a mathematical black hole? A mathematical black hole is one in which if you fall in, you never ever get out. But how will you ever know that you will never get out until you look at the entire future of the universe? Now, if the universe is closed, spatially closed, so its mathematical term is spatially compact, then it is possible to have a universe with no event horizons. On the other hand, if it's non-compact, then you can...
I've lost your voice.
Let me try again. As I said, if I have to hold the key down and then release it periodically, I can't go into a long talk here. The point is that if the universe is spatially non-compact, we say it's open or flat, then you have to have event horizons. That is a theorem. So I conclude from this that the universe has to be spatially closed, which means it's finite in size spatially. You can also use more complicated considerations in physics and conclude not only is it spatially compact, but spatially it must be a three-dimensional sphere. That gives you some information about the boundary conditions. I could talk for hours on this, but that's a rough summary.
Thank you so much. Let's move. Yes, it's actually a continuation here about the fact of whether we already have a final theory of everything or not. You say yes, but don't you think that future development could revolutionize current physics, just like general relativity and quantum mechanics revolutionized physics, even if on second thought you seem to think that the revolution of general relativity and quantum physics wasn't that big a revolution, and in fact the 19th century physicists like Maxwell, Poincaré had everything basically right. That seems to be your idea. That sounds kind of revolutionary in itself, so maybe you can say a few words about that.
Let's take quantum mechanics first. Of course, what I'm going to conclude is what you've just said, that neither general relativity nor quantum mechanics were a revolution away from classical mechanics. Quantum mechanics is the easiest to demonstrate that that's true. Although currently it's considered more revolutionary than general relativity. The opposite is true. And I published a detailed proof of this 2 years ago in an article in the Proceedings of the National Academy of Sciences. Basically, quantum mechanics is Hamilton-Jacobi theory. The Hamilton-Jacobi equation is really already includes inside it the Schrodinger equation, which I think everyone, certainly I think, that the Schrodinger equation has within it all the essence of quantum mechanics. Other equations are just throwing in relativity. Quantum mechanics is fully there, all of its crucial aspects in the Schrodinger equation. Now, if you consider the Schrodinger equation, the Hamilton-Jacobi equation, that was certainly considered to be the ultimate expression of classical mechanics in the 19th century. Now, what I've been able to do is trace the Hamilton-Jacobi equation back to Newton himself. Newton knew, and this was a point made by Thomas Young of the Young double slit experiment, which everyone considers correctly to be a proof of, first, the wave nature of light, and second, when you send electrons through a double slit, they start showing an interference pattern. So it also justifies the wave nature of electrons. It justifies wave nature. When Young first published his double slit experiment, double hole experiment to be more precise, he never got to the slits. But he could see the interference pattern with the holes, had argued that light was particles and not waves. Young came back with a statement, and he justified this in a paper he published around the time of the war, the what we call, well, I think of it in terms of the Battle of New Orleans. Said being a professor at New Orleans, at the time the Battle of New Orleans was fought, about that time, Young published this paper in which he demonstrated that Newton believed that light was simultaneously particles and waves. And Newton said in one of his queries that, sorry, my computer went down again. Newton said in one of his queries in his optics that he thought that light should be considered a wave and a particle, but he did not know how to turn light into a wave theory. Now, Hamilton was the first one who actually achieved showing how light could be a wave theory, and his theory was simplified into a single equation by Jacobi, which is why we now call it either Hamilton-Jacobi theory or the Hamilton-Jacobi equation. And this captures both the wave and the particle notion that Newton sorts of particles. So right there in 1840, when Hamilton and Jacobi worked it out, there are particles and waves in mechanics, in classical mechanics. You take a book on advanced classical mechanics, they will always have a section on Hamilton-Jacobi theory. What is Hamilton-Jacobi theory? Well, there are particles, obviously, but how do they connect with waves? What the Hamilton-Jacobi equation is really a wave equation, and in the wave equation, the wave moves with time, and it is held that the trajectory of a particle is a single path that is always perpendicular to that particular wave, the Hamilton-Jacobi wave. But if you look at the equation, there's no reason to single out one particular trajectory over another. Rather, they are all really real, equally real, which is to say, right here, you have many worlds appearing in classical mechanics. Let's accept that the Hamilton-Jacobi equation is, in fact, a many worlds theory, and let's use the Hamilton-Jacobi equation to prove that those other worlds exist. How do you prove that anything exists? Well, you are convinced that I exist because you're seeing and hearing me right now. Sound is being generated by my mouth and going over the lines and hitting your ears. If I were physically present, what I would do to prove my existence is I would hit you. Very lightly, of course, but I'd still hit you. That's how you become convinced anything physically exists, if it can hit you. Think Dr. Johnson kicking the stone. All right, let's go back to the Hamilton-Jacobi equation. Let's consider the wave moving, the Hamilton-Jacobi wave, moving around an attractive potential. Now remember, the normal to the trajectories, which are everywhere perpendicular to the Hamilton-Jacobi wave, such trajectories on one... Sorry, computer shut down again. On one side of an attractive potential, it would be curved toward the attractive potential. Now think physically about an electron moving past a proton. That's the way you want to think about this. Proton, positive charge, electron, negative charge, attractive potential. Attractive force between them. So the electron on one side is going to be curved toward the proton by the electrostatic attractive force. On the other side of the proton, it's going to be attracted again toward the proton, but in the opposite direction since it's on the other side of the proton. Now follow these trajectories and you will see, if you work through the calculations in the Hamilton-Jacobi equation, that they collide on the other side. When they collide, that means the Hamilton-Jacobi equation no longer applies. Incidentally, it establishes, from the Hamilton-Jacobi equation point of view, that other trajectory actually exists. It just clobbered your trajectory into non-existence. Boy, that's a real clobbering. But of course, reality is not like that. That would mean a breakdown in determinism. If you had a collisions of these two particles. So let's try to correct that. One way you can do that, and I think this is really the only way, but I don't know how to prove this mathematically, I just conjecture it, is to add another potential of a certain form, and I described how you do this. It was actually, this potential was discovered independently by Bohm and Landau decades ago. So in doing this, using this particular potential, I'm doing nothing new. But with this potential and another equation which says that the trajectories are conserved, and in order for the theory to be fully consistent physically, they have to be conserved. I could go in detail and describe why, but this is getting too long as it is. With this equation plus the added equation, you can then prove that the Hammond-Jacobi equation plus the conservation equation and the modified Hammond-Jacobi equation, which you've added this new term, new potential term, these two equations together are fully mathematically equivalent to the Schrodinger equation. The Schrodinger equation, in other words, is just the Hammond-Jacobi equation upon which you have imposed the condition that determinism is globally true. The Hammond-Jacobi, the Schrodinger equation can never develop these caustic singularities because it's a linear equation. That incidentally shows you why quantum mechanics exists. Quantum mechanics is there to prevent the formation of singularities in the laboratory, and it also shows you why the Schrodinger equation, more generally anti-quantum equation, is linear, once again, to avoid the formation of singularities in the laboratory. In other words, quantum mechanics is there to ensure that reality is fully deterministic. Einstein got it right. God does not play dice with the universe. Now, this procedure requires you to take a different view of the meaning of the wave function. In textbooks of quantum mechanics, we were told that the wave function is a probability amplitude. Feynman correctly said, goodness knows what that really means. It turns out that if you find out the logic of what it means experimentally, it just means in the limit of an infinite number of observations that you will have certain frequencies of possibilities. Now, from the point of view of this approach that I've outlined, which is intrinsically many-world,
and some white noise.
Can you hear me now? I don't know what the problem is. I've just not done anything as far as I can tell to the microphone. Are you still getting the white noise?
Yes, just perhaps lift the finger from the control key and don't hold it for a few more seconds. I'm just thinking aloud. By the way, what you're saying is really, really fascinating. I had seen the paper in PNAS that you mentioned. I must go back and read it carefully again. Oh, now I will take advantage of the post to make a comment. I'm wondering, in fact, if all that means that somebody like Hamilton in the 19th century could have deduced the need for quantization without experimental evidence, but only on the basis of the consideration that you just made, and perhaps using a mathematics that had not been developed that time yet. Okay, let's see if the white noise problem is solved.
Let me reply to what you just said. You're still getting the white noise?
Yes, ma'am. Micah, can you switch your microphone off?
What about now?
Still white noise.
Still white noise. No, let me try to turn my microphone off on the screen and then turn it on again and see if that helps.
or you can just go to Tools, Sound, and Reset Sound. I'm going to do that too.
I've tried to
Tools,
reset.
Sound, Reset. And
okay, good.
in fact, I'm not hearing white.
Can you hear me now? White
Yes,
noise?
I can.
Yes, I can.
And
White
no
noise? And no white noise. Ah, good. All right. Okay, I just had to turn off the phone. Okay. Now, I have another paper which I'm not yet even put on the archive yet, in which I go into this discussion about how quantum mechanics arises from requiring a full global determinism in classical mechanics, in a paper in which my main thrust is deriving the Heisenberg uncertainty principle by showing that the system is not uncertain. Rather, what happens is we lose our ability to predict because of information coming into our universe from the nearby universes. That's the main thrust of the paper. But I go into more detail in showing that you do not have a choice in what the wave function is. Namely, what historically has happened is, of course, Schrodinger wrote down his wave function, his wave equation, in many ways just by guessing, after which Born came up with his interpretation. But in this case, this approach, the interpretation of the wave function comes with the derivation of the Schrodinger equation itself. It is a universe density amplitude. It measures the relative density of universes in the multiverse. You don't have a choice. That's what it is. And in answer to your question, could 19th century physicists have discovered this by pure mathematical considerations? I think unquestionably the answer is yes, because in this new paper I show exactly how that could be done. You will have a new universal constant coming in, which has the units of action, and what it measures is how much effect the universes have to interact with each other to keep the singularity from appearing in the universe, in any universe. So that's the real meaning of the Planck's constant. That's what comes from, as I say, the derivation. I had some of this in that Proceedings of the National Academy of Sciences paper, but in far more detail in this later paper that I mentioned. The upshot of this is I agree with you first that they should have discovered this, and actually I have heard, but I've not been able to confirm, that there was a discussion between the great mathematician Felix Klein of the Klein bottle fame and Schrodinger himself, in which they wondered why the Schrodinger equation was not invented in the 19th century. And their conclusion is because physicists at the time did not take the equation seriously. They used it simply as a technique to easily find solutions to classical mechanics problems that interested them. They never studied the equations and its full implications itself. Now, it is a pity that Maxwell did not died so young of cancer, because he was beginning almost to discover quantum mechanics from a different direction. I have a discussion of this in my book, The Physics of Immortality, in which I'm discussing the questions of if you make a perfect copy, it is the same with the original. That is an aspect of indistinguishability, which was first noticed in the 19th century in the form of the Gibbs paradox, and Maxwell was following up on that, and he realized that the full implications of this, what is now considered quantum mechanical property, but is really there in classical mechanics, was that, excuse me, that in certain cases energy had to be quantized. It had to appear in one of two values. It could not be anything in between. And Maxwell wrote about this for Encyclopedia Britannica, and he left it off. I don't understand this. I thought energy had to be continuous. Unfortunately, before he could follow up on this, he died of cancer. So we missed the chance in the 19th century, but we will eventually get the chance at long last to realize the full relationship between classical and quantum mechanics. As I've just argued, quantum mechanics is not a revolution at all. It's just fully accepting the full implications of classical mechanics, and the basic idea goes back to the great Newton himself. As regards general relativity, let's now discuss GR. I don't consider it a great breakthrough either. It was just that people did not understand the mathematics of either. Computer shut down again.
Yeah.
Can you hear me?
Yes.
Yes.
In the meantime,
I want to the realization that
perhaps
instead of writing that general relativity was revolutionary, I should have written that also special relativity was.
Special relativity is just an automatic consequence of the Maxwell equations. Maxwell proved in, I believe it was 1859, middle of the 19th century, that the speed of light was 1 in the vacuum, 1 over the square root of epsilon 0 mu 0. Epsilon 0 mu 0, permittivity and permeability of the vacuum, are universal constants. Therefore, it follows that the speed of light is a universal constant too. In other words, the speed of light has to be independent of the observer. Now, Einstein, in his 1905 paper, just started with that. The speed of light will be exactly the same for all inertial observers. That gives you all of special relativity immediately. And furthermore, Maxwell and Poincaré and Maxwell proved that if special relativity holds, then necessarily there will be a 4-dimensional metric. Now let's go back to general relativity, which is a theory of gravity. That's the difference between special relativity and general relativity. Special relativity has the curvature 0 everywhere. General relativity, of course, has curvature. Now, the great French mathematician proved around in the 1920s that, in contrast to what everyone thought, Newtonian gravity theory is also a theory of curvature. And he wrote down the Poisson equation in curvature language. The components of the Ricci curvature in the time direction were equal to 4 pi g times the density. That's equivalent, that's the same thing, a re-expression of the Poisson equation in curvature language. All the other components of the curvature are 0. Now, there's curvature, in other words, only in the time direction in Newtonian gravity theory. Curvature is 0 everywhere in space. However, this was a view which physicists adopted only because they were not aware of the possibility of curved space. Of course, Riemann, Lobachevsky, and so forth pointed out that space could be curved, and in his habilitation lecture, Riemann said, I think that curved space should be fundamentally a curved space based on the 3-sphere. His teacher, the great German mathematician Carl Friedrich Gauss, was in the audience, and he totally agreed with Riemann that the universe has to be, computer shut down, has to be a 3-sphere. So basically this insight of these 19th century great mathematicians is really now finally just following out of the physics. But let's now combine this previous insight which we got from the Maxwell equations and Einstein. But again, Einstein realized this fact about the Maxwell equations in 1905. Independently in 1904, Lorentz realized the same thing. Einstein's derivation was prettier. They were independent though. All you need is speed of light constant for all observers, special relativity gives you that automatically. But it also means that you no longer have, the Maxwell equations imply that you no longer have absolute time. That means that it is possible to mix spatial curvature, which remember we already have from Riemann and Gauss, with curvature in the time direction. They can no longer be separated. Now, if you restrict the theory of curved Newtonian gravity to be such that the curvature arises entirely from the metric, which was no longer possible when you had absolute time. Special relativity now has destroyed absolute time. Now that you combine the two, you have to combine the two if special relativity is true. This curvature in time and curvature in space. Then you look for a new equation which equally restricts gravity, and you find out that there is a natural, unique solution which is consistent with the conservation of energy. Lo and behold, that equation is the equations of general relativity. So, for this reason, I would regard general relativity is really, once you've combined Newtonian gravity theory with the Maxwell equations, both of these equations are considered classical equations, automatically general relativity follows.
Oh, only thing I can say is extremely interesting thing. Let's move on. Not to take all your time. Oh well, that's really a challenge for. Could you lift the control key? If you keep holding the control key, I'm hearing the echo.
I was not holding the control key. We might have to restart the sound system again.
No, okay, let's. So now you're not holding the control key.
I was not then.
Okay, then do the restart again. Tools, sound reset. Sound has been reset. Okay, then I think you should right-click the microphone and choose to talk again. Choose to talk again.
I think we're okay. Can you? Are we having any problems now?
Echo? Yes, echo. So what I'm going to do, use push to talk myself now. No, that wouldn't help. Okay, I'm not hearing the echo now, which is good. So, okay, my next question was really a challenge for a physics professor. That I'm wondering whether you could explain as simply as possible just what is the Wheeler-DeWitt equation that you mentioned before, why it is so important, especially what does solving the Wheeler-DeWitt equation mean, especially in view of the fact that it doesn't contain time as a variable.
As you correctly pointed out, the Wheeler-DeWitt equation is an equation for quantum gravity. Now, all quantum mechanical equations are equations for wave functions. Now, what are the arguments of the wave function? That is, what is the wave function a function of? In the Wheeler-DeWitt equation, it is a function of the three metric, that means not four-dimensional, but three dimensions, which are the spatial metric only. As you say, it does not contain any relevance to time, at least not directly. It is also the wave function in the Wheeler-DeWitt equation. Not only is it a function of the three-metric, it is also a function of whatever matter variables you have around, which are controlling the spatial metric. Now, in my particular case, I noticed that some Russian physicists had realized that with a particular sort of collection of matter variables, which were natural to the early universe, which you expect to have very high homogeneity and isotropy, i.e. very close to a Friedman-Robinson-Walker metric, that there was a natural choice of the matter variables that would effectively represent time. In other words, you are representing time by a collection, by how the matter variables appear in a given space. What that particular choice of matter variables will do is order these three metrics, and the order of the geometries, the three geometries, collectively ordering them together. Think of having little thin disk which you are piling on top of each other. The thin disk represents the three metric, and the particular pile you represents how time appears. Now, with a particular choice of matter variable, there is a natural piling of the disk, a natural ordering of the three metrics that effectively represent conformal time. That's a conformal time is a particular choice of time which we physicists who are doing cosmology problems naturally use. Now, we've noticed in cosmology that if you use conformal time rather than the usual time which we are used to using here on Earth, sometimes called, my computer shut down again, sometimes called proper time. I can go into detail what the distinction between the two is, but from our point of view at the moment, conformal time makes the equations in our particular universe simpler than using regular time. So typically what we do when we're trying to solve our equations in cosmology at the classical level is we switch over to conformal time. What I'm proposing is let's do this quantum mechanically. Let's use the same conformal time to order these disks in the wave function. Effectively then, the Wheeler-DeWitt equation will then include time because we've made a choice of the matter variables to effectively represent time. And so what we will have is remember this is a quantum mechanical equation, so it's intrinsically many worlds, and what this conformal time then is the universal time across all the universes in the multiverse. So what we're having is the Wheeler-DeWitt equation is telling us how each individual universe is evolving collectively with each other in the whole multiverse. Now, if the universe is radiation dominated, that is, radiation is the most important part of reality. Now, everybody thinks, and I think so too, that that is true of our universe. And as I've outlined in the Physics of Christianity, I gave you evidence there why it is. And I did also in my 2005 paper. Then the Wheeler-DeWitt equation becomes mathematically identical to the non-relativistic Schrodinger equation for the simple harmonic oscillator, which we all know and love. We physicists are trained in college, elementary school, almost to solve the simple harmonic oscillator equation. So this enormously simplifies the problem of quantum cosmology, because now you have an equation for the full multiverse, which is just the Schrodinger equation for the simple harmonic oscillator. And what I'm proposing is things look particularly nice if we assume that initially the universe was a delta function at the initial singularity. That means all the universes in the multiverse began at the same conformal time 0, and expanded out from there. And as I've said, this naturally solves the flatness problem because a delta function will explode outward. That's quantum mechanical wave packet spreading. We've seen it many times in the laboratory.
I have lost your voice.
I'm back on again. Is it okay now?
Yes.
Yes.
Okay. Now, the point is that if the wave function of the universe would explode outward, and almost all the universes would be extremely large. That's why, although the universe would be closed, spatially closed, I've already mentioned earlier in this discussion why it has to be closed in order for quantum mechanics to be consistent globally throughout all time. But given that it's closed, it obviously has to be extremely close to flat. That means the sphere, which corresponds to the universe, must be very, very large. So we can't notice the non-flatness. We've measured the curvature of the universe, and indeed, the Planck experiment and the WMAP experiment shows the universe to be very close to flat, to at least 1 point in 100, possibly now 1 point in 1,000. I'm predicting 1 point in, it's close to better 1 point in a million. But the point is that the explanation in this case for why the universe is flat is wave packet spreading. Wave packet spreading we've seen in the laboratory. We have never seen an inflation field in the laboratory. So this explanation explains this important observation, resolves this important problem of cosmology using physics, which we already know. Now, this has been my entire approach in all this, is using physics that we already know. We don't have to use new physics. So it's unlikely, I claim, there is any more physics. We don't need it for anything.
Very interesting, and I think you have anticipated one of my next points. Yes, in fact, this about dark energy. You just discussed that. So you can explain the measured cosmological constant and why its value is so dramatically different from what can be computed with quantum field theory.
I think what people are doing is they are using quantum field theory in putting it in a realm in which it's not. The standard quantum field theory is not valid. And remember that we know that standard quantum field theory is not valid. It's only when you throw in the final boundary conditions that makes it consistent that you can use it. So they're using, when they're getting a huge cosmological constant, regarding the cosmological constant as the energy of the vacuum, they're getting a huge value because they're not using a fully consistent version of quantum field theory. When you're computing the energy of the vacuum, you have to use a fully consistent quantum field theory. Well, let's do that. One of the things we know is that when you do the calculation, you cannot have a really large value of the cosmological constant, because if you did, and positive value, which it has to be, then you would have the universe accelerate forever. Accelerating forever means that the final singularity will not exist at all. That means that you cannot have consistency in quantum field theory and having a really large cosmological constant. You have to have a relatively small cosmological constant. How small? Well, you can say something about that too. First of all, you know that the Higgs energy field, which we know exists, also will contribute to the vacuum energy, and we have an estimate for what that value has to be, actually a pretty good measurement of what it has to be, now that we know what the value of the Higgs mass is. So you know you have to have a positive cosmological constant, and it has to be very, very close to the Higgs vacuum energy, which is, interesting enough, in our phase of universal history, will look very much like a negative cosmological constant. That is, a cosmological constant which is negative rather than positive, which comes up from quantum gravity. And in order to have consistency of quantum field theory, these two values have to be very, very close to each other. Right now, obviously, the positive cosmological constant coming from quantum gravity is slightly larger than the a negative cosmological constant coming from the Higgs vacuum. Now, the interesting thing about this is that in the current environment in universal history, this combination of the Higgs vacuum, but with the Einstein, with the quantum gravity cosmological constant, computer shut down again, will give you a net positive cosmological constant. But remember, this positive cosmological constant has to be turned off. Now, that is allowed from the fact that you have part of this effective dark energy, which looks very much like a cosmological constant in the present environment. It has to be capable of being turned off. That's what role the Higgs vacuum is going to play. You can adjust the Higgs vacuum by activities which intelligent life can perform and cause it to become greater than the positive cosmological constant from quantum gravity, with the result that the overall energy density of the universe then becomes positive, and recollapse of a closed universe then becomes possible, and it has to occur simply because otherwise quantum field theory would not be consistent.
Well, I think you anticipated my next point again. And in fact, well, that was a lot of theoretical physics. Let's talk some engineering, some simple, honest engineering. What should our descendants do? And how?
In the short run, and I'm going to anticipate in answering this some other questions you have. First of all, I think that the number of intelligent beings in this universe will be very small, and depending on the exact mechanism of how you turn off the cosmological constant, the dark energy, we may be unique in this universe. Now, the reason for having us unique is that if there were too many intelligent life forms around, we would use up the energy too fast. Right now, in the current phase of universal history, in the expanding phase, the ultimate source of energy is matter, converting matter into pure energy, and that is allowed by the Standard Model. I mentioned earlier in this conversation that the Standard Model has a natural mechanism for baryogenesis, that is, creating baryons rather than antibaryons. Effectively, what you're doing is you're turning energy of the radiation field, which began the universe. Remember, in the very, very, very early universe, at the beginning of time, there was nothing but an SU2 left gauge field. That gave rise to baryons. The Higgs field started to take on its vacuum, its non-zero value, and eventually it damped out. So now it's doing just minor oscillations around its 0 point, around its vacuum energy. Incidentally, those
lost voice.
What about now?
Now is good.
All right, those oscillations of the Higgs vacuum, which has to exist under my theory, very small oscillations, but they're there. We've known for 30 years that those oscillations of the Higgs vacuum, that by itself would give rise to an energy field that behaved as if it were matter at zero pressure. But it would not interact with regular matter electromagnetically, it would just interact gravitationally. So incidentally, we have falling out of the Standard Model a natural explanation for the dark matter. So we've not only got dark energy, we've got an explanation inside the Standard Model of dark matter too. Dark energy, dark matter, all accounted for in the Standard Matter, on the Standard Model of particle physics plus Standard quantum gravitation. All right, now, this mechanism in the Standard Model gives you baryogenesis. Energy is being turned into matter. The process can be reversed, and our descendants will do that. That's the ultimate form of energy, which our descendants, will use as we expand out from this planet, which we must if we're to survive. We know that this planetary system of ours is not going to last forever. At most, our sun can provide energy for the biosphere for an upper bound of 10 billion years. My guess it'll be more like under a billion years, but that will not happen. Our descendants will long since have left this planet and taken apart our planet, the other planets of the solar system, and our sun, converted it into living space for themselves, and start to convert the material of the solar system into energy to provide for their lives. You need energy in order to live. We will, of course, expand out from this solar system, ultimately to engulf the entire galaxy and the nearby galaxies. Now, this conversion of matter into energy will have the incidental effect of turning off the dark energy, its repulsive features, and how fast we do this will answer the question of whether or not there needs to be another intelligent life form out there in order to turn off the dark energy in their neck of the woods. I do not know the answer to that right now, but I do know this. There can't be too many intelligent life forms out there, because remember, the ultimate source of energy for any intelligent life form is going to be the conversion of regular matter into pure energy, which is allowed by the Standard Model, which the Standard Model used which was used in the early universe by the Standard Model to generate the matter, which now go to make us up. Now, of course, in talking about our descendants, I'm thinking here more about our AI and human download descendants, our computer descendants, we could call them more generally. They will be the ones which move into beyond the solar system into interstellar space. I think that the development of artificial intelligence at the human level will occur sometime this century. I don't think that we, as human beings at the lowest level of implementation, will ever move out in any significant way into space. I think basically in the near future, all of us will convert into human downloads and, of course, live forever as we move out into the universe. Now, the laws of physics are set up so that in order to survive, knowing the laws of physics, we have to act in such a way that will ensure a good outcome. I've described what we will do in the near future, namely the next 1,000 billion years. We're expanding out from our current planet, engulfing the universe which we can. Then once the universe universe has reached its maximum size and started to recontract, then we will have more or less used up all of the matter. We need another energy source, not only to provide energy, but to reverse the process and create the matter, however we decide, our descendants decide to do it, create the material upon which we will be based, and that will come from gravitational collapse itself. As the universe collapses down into the final singularity, into the omega point, then the source of energy from that time on, from the time of maximum expansion to the final singularity, will be gravitational collapse energy. Now, we will have to have engulfed the universe into, in its whole, we will have intelligent life by this time will have had to take over the entire universe, because in order to access this gravitational collapse energy, you will have to manipulate the universe into collapsing preferentially more in one direction rather than another. And I describe in detail how that will need to be done in my book, The Physics of Immortality, and outline in the regular section for the non-technical person in more technical detail in the scientific appendix, which I give all of the equations.
I understand that it sounds like a very good project for the future of our species, but why do you rule out the possibility that a lot of other civilizations are doing that at the same time? And in fact, I mean, they don't even need to be that many, it could be just one. Also, suppose one alien civilization is starting about now to embark onto a project to re-engineer the universe to ensure an omega point future. They don't need to be that advanced. Suppose they're starting now. Is there any observation that we could do that could give us some evidence for alien civilizations re-engineering the universe in this sense?
Well, I've already given the argument why I think that alien civilizations, even at our level of civilization, or indeed any rational beings other than ourselves, I think they're going to be very few. And the reason is the very physics itself. Namely, that as the laws of physics are now set up, there would be a tendency of beings, if they were very common, to use up the matter too fast. Right now, if we are, say, the only intelligent life form in the universe, then we cannot move out faster than the speed of light. We can't take over the universe too fast to use up the energy supplies of the universe. So the laws of physics are set up to allow us to use the energy which is just at the right speed. That's why we can be assured that ultimately the singularity is benevolent, because it's set up in such a way that we are assured that we can't do too much, but we are forced into doing just enough. We're going to be encouraged to do just enough. We have to do it in order to survive, but we can't. The laws of physics can be counted on, the speed of light barrier can be counted on to prevent us from using up the available energy too fast. If there were too many intelligent species out there, then there would be a tendency, unless they showed self-control. I prefer to have the laws of physics restricting what intelligent life can do, rather than depending on intelligent life showing self-control. So that is why I think intelligent life forms are going to be very rare. Now remember that the whole system now is deterministic. Remember, the wave function is not a probability amplitude. The wave function is a universe density amplitude, density of the universes in the multiverse. That's what it has to be, given the derivation of the Schrodinger equation from the Hamilton-Jacobi equation. We don't have a choice of what the wave function is. Incidentally, I show in my Proceedings of the National Academy of Sciences paper that you can derive the Born rules from the density of a universe's amplitude interpretation. Although it's not just an interpretation, because that sounds like you have an option. You don't have an option. The wave function is a measure of the density of universes in the multiverse.
Yeah, interesting. I'm kind of surprised to find out that you are quite pessimistic about at least the density of advanced civilizations in the universe. For some, I guess, psychological reasons, I like to think that there are a lot of civilizations out there.
I think you're wrong.
Okay, I hope I am not, but let's...
Laws of physics are whatever they are. And if I am right, more calculations will throw more light on my claim that intelligence has to be very rare. Now, it has another advantage. If intelligence is rare, think about the full implications of the rarity of intelligence, and also the fact that the universe is deterministic. If intelligence, remember, in this scheme I'm deciding, we have to be there. We have to be near the final singularity. Our descendants have to be there. Otherwise, you can show that the second law of thermodynamics would not be consistent throughout all time. So we are brought into existence in part. We will do our part to ensure the consistency of the laws of physics themselves. Everything in the universe is there for a reason, and everything in the universe is there to ensure mutually that the laws of physics are mutually consistent. We humans have an unfortunate tendency to consider ourselves as standing outside the universe, standing outside the laws of physics. No, we are fully subject to the laws of physics, but the laws of physics are there ultimately depending on us to do our thing. So if we are essential to the final singularity, then that means we cannot destroy ourselves until we have given life to our descendants. Now, if there were other intelligent life forms out there, and they were fairly common, the argument I've just given you says that most of these intelligent beings would have to be wiped out, kill themselves, suicide of their civilization, destroy their entire species. I find that more depressing, the inevitability of the extermination of most intelligent life forms, rather than the scenario I'm proposing, in which God, let's use theology here, is benevolent, and he does not want to have more deaths than strictly speaking necessary, so he gives rise to us, and he will assure that we do not destroy ourselves. We can do a lot of damage to ourselves, but total annihilation, in spite of appearance, is not possible. God's going to arrange it so that it doesn't happen, at least until we give rise to our AI descendants.
Okay, but I think there is also a different argument. I'm going to keep that short because, I want to focus here on what you think, not on what I think. But, suppose there are many civilizations in the universe. Now, all of them will be able to use exactly the same logic that you have just used, reach the conclusion without any necessary coordination. Everyone reaches that conclusion for themselves. That intelligent life in the universe have to cooperate to guarantee a good outcome for the universe. And in fact, that would be the equivalent of many different civilizations all together evolving toward the omega point. I do find that scenario aesthetically very nice.
But you're not paying attention to my crucial argument. Excuse me. That we would collectively, if there are too many, use up the resources of the universe too fast until the recollapse begins and provides us another energy source. That's the problem which we have to look out for. Now,
not if there is some coordination.
But remember, the light barrier is going to prevent direct coordination until the collapse begins. As you've just said, if there are other intelligent life forms out there, then these intelligent beings, which act under the same laws of physics that we're acting on, will draw the same conclusion that I've just drawn.
Yeah.
Necessarily, they'll do that. And they will begin the expansion in just the way I have described. Now, as I mentioned earlier, it depends exactly, very closely, on how the turnoff of the dark energy actually works. According to the standard pictures now, the standard pictures, there will have to be other intelligent life forms out there, but they're probably on very far out there. Most of them will be outside of our current event horizon. So, excuse me, our particle horizon. So we would not be able to see them directly at the present time. It would only be in the collapse phase of the universe in which coordination, which is, so to speak, pre-established, because they will be doing their thing independently of us, but they will be acting on the laws of physics known to them just as we will be. And once the collapse begins, then we become in contact, and then we can start working cooperatively. But this whole game works only if in this phase of universal history, right now, in fact, we are relatively rare. Certainly, we are by this argument, certainly we are the only intelligent life form in our galaxy. Probably we're the only intelligent life form in the local group, and depending on exactly how the binding of gravitation right now is, and this we do not have detailed information, probably we would be the only life form in the Virgo cluster. Beyond that, I simply don't know. But if the current data we have at the moment indicates that you are right, there would be other intelligent life forms out there. For example, one would probably be at the antipode of the universe. But you and I, and the present near future, are not going to communicate with them. We can talk to them as human downloads, something like 1,000 trillion years into the future as human downloads, but not in the near term. Next few centuries will we ever communicate with these beings. They are simply too rare. As I said, certainly not in this scenario are there other intelligent beings in this galaxy, and certainly not in the local group. Computer died.
Let's hope that.
Computer died again. But again, this is assuming that we are not, that the typical fate, one assumption I'm making in this is that the typical fate of an intelligent species is not to exterminate themselves. If that does not occur in general, then they are rare. On the other hand, if this is the typical behavior of an intelligent species, that they wipe themselves out, then they could be out there in great numbers. Because if they wipe themselves out before they begin the expansion, then they will play no role in universal history. The way our history runs, we are so close now to beginning the expansion that I do not think that we will wipe ourselves out before we begin, before we create our human downloads, learn how to do that, and create artificial intelligences. I don't think that will happen. Now, this is based on just physics analysis, but of course on theological analysis, if I'm allowed to bring that in, I think that God is good, and he will not allow more intelligent life than absolutely necessary, because he does not want intelligent life to extinguish themselves.
Okay, Thanks so much, and let's move on. Oh yes, that's a nice point. Now, suppose that doesn't work. Maybe the physics doesn't work, maybe the engineering doesn't work, maybe God doesn't want. Okay, suppose that doesn't work. Suppose the universe keeps expanding forever. Now, you said in the interview with Micah a couple of weeks ago that you liked very much Freeman Dyson's article about how intelligent life could survive forever in an open universe that keeps expanding forever. Now, is that any version or modification or tweaking of your scheme that would work in that scenario?
My work on the omega point theory, intelligent life going on forever in a closed universe, was inspired by Freeman Dyson's time without end. The problem with Freeman Dyson's scenario is that, as Freeman Dyson has himself said, and he's absolutely right here, it will not work in a universe that accelerates without end. So in order for his theory to work in what you call an open universe, that's a non-compact infinite universe, spatially infinite universe, then if it accelerates forever and the acceleration continues as it is currently measured to be with that value, then life will become extinct in Freeman Dyson's scenario. And Freeman Dyson, as I said, knows as well as I do, he said many times, that it's a disaster if the universe accelerates forever. You have to distinguish between an ever-expanding universe with decreasing velocity, which is what Freeman Dyson had, and a universe that's accelerating with ever-increasing velocity. You get wiped out in that scenario. Now, I find Freeman Dyson's model ultimately rather depressing, because he never expands to engulf the entire universe. It's not as inspiring, I think, as mine. And the universe just gets darker and darker. He manages, nevertheless, to eke out a survival without limit, for infinite proper time. This is assuming he has a mechanism to turn off the acceleration. And remember, I do, but the acceleration turn-off mechanism is intimately connected with the fact that the universe collapses into an omega point. And also remember a problem.
You lost your voice.
What about now? Can you hear me?
Now good. Yes.
Freeman Dyson gave up on his work in quantum field theory because he proved that this series expansion that Feynman used for the Feynman diagram was ultimately just going to give you an asymptotic series, which means that literally everything predicted in that theory gives the answer infinity, which is obviously false. So Freeman Dyson realized his own theory of quantum field theory was going to be inconsistent. My alternative, which makes it consistent, requires there to be a final singularity. So Freeman Dyson is going to have to provide an alternative quantum field theory in order for his game to be played. But as I've said, psychologically, his universe, in which life does manage to eke out a survival to the very end of time, really doesn't seem to have any purpose in it. Is not very, well, let's say, moving or exciting. In my case, we ultimately take over the entire universe and control it, growing in power without limit. Our power expands without limit as we're going into the final singularity. Much more uplifting than Freeman Dyson. Now, Freeman Dyson says he was motivated because he does not like a universe to be bounded in any direction. He said unbounded in all directions. That's what motivated him to have an open universe. But his universe is still bounded because we do not live in space alone. we really live in phase space, which is not only spatial space, if I can use that phrase, but also momentum space. Phase space is traditional space and momentum space together. In Freeman Dyson's universe, the momentum direction becomes narrower and narrower as you go into the far future. Indeed, you have infinite space, but even then, you are never going to engulf the entirety of your infinite space. So you're bounded in really ultimately both directions. In mine, you engulf the entire universe, finite though it be in space, but it is unlimited in the momentum direction. The momentum direction expands, in other words, near the collapsing phase more rapidly than the space contracts. So momentum space is growing ever larger. Total phase space is growing ever larger. But in Freeman Dyson's universe, the inhabited world is expanding but never going to infinity in the spatial direction, and it's growing more and more narrow in the momentum direction. So I claim that Freeman Dyson's universe ultimately fails on its own criteria set up by Freeman Dyson himself, namely he wants it to be infinite in all directions.
Good. What do I have now? Oh, well, let's. This is not very relevant to this discussion, but just by curiosity, do you still like your cylinder idea for a time travel machine? And do you think sometime in the perhaps far future, our descendants could be able to engineer something like that?
Nope, I gave up on the cylinder, which I published in 1974.
Yes.
I gave up on the cylinder in 1976, in which I proved that you could not create a cylinder speed one up by any means without ripping a hole in space-time, without having a singularity in space-time itself, which would make quantum field theory inconsistent. So I do not believe that that's possible. However, my argument would be, why would one want to create a cylinder and go back in time? Remember then the far future, when the resurrection is carried out. The resurrection is going to reconstruct in the computers of the far future past that ever existed. So in the far future, you as a human download or a resurrected human download are going to be able to experience all past that ever existed. In the far future, in other words, you will not need a time machine.
Okay.
All the times, all the past will be there for your access.
Great. In fact, the best type of time machine is not needing one, I guess.
Exactly.
Okay. I think I have one last point about physics before a few points about theology. I think you already discussed that. Perhaps you could just quickly summarize your best argument in favor of Everett's interpretation of quantum mechanics. And I am curious to know what you think about the many minds formulation that, according to some, including myself, may be closer to what Hugh Everett actually had in mind.
One could argue ever forever over what Hugh Everett had in mind. But Hugh Everett would agree with me in this. What is important is not what an individual has in mind, but what is reality actually like. And I've given you the argument that the many worlds are already there in classical mechanics. Many worlds, by implication, if not realization, was there in Newton's own view. He knew that light had to be both a wave and a particle. Particles of light, particles which are electrons, we know what they are. What are the waves? They are electrons or particles of light moving in concert across the many worlds. That's what they are. That's what the Hamilton-Jacobi equation says. That's what the Schrödinger equation says. So I think reality says many worlds. Many minds is a implication of the importance of minds. But these worlds are acting before minds came into existence. I described for you why the best explanation for the flatness problem, remember it comes entirely from quantum mechanics, from wave packet spreading. This occurred, this action of the many worlds occurred before minds even came into existence. Now, taking many worlds and neglecting minds, just considering physics without minds, has all sorts of very interesting experimental consequences, because many worlds theory, as I've already described, contains a delta function as a perfectly acceptable wave function. But a delta function is not a function in any Hilbert space. Therefore, it's not allowed in standard quantum mechanics. This shows you that many...
I've lost your voice.
What about now? Do you have my voice again?
Yes.
All right. This shows you that standard quantum mechanics is not equivalent to many worlds quantum mechanics. This has quite a number of experimental implications, some of which I'm working on now, and we'll see results of that. It's a separate experiments, separate series of experiments from the one I described to confirm how the universe began. But I'm not going to take the time to describe it now. Take too long.
I look forward to reading about that. And I think let's come to some final point about theology. Okay, so in the physics of immortality, you have the role of a God made by intelligent life. And as a matter of fact, as you just explained, by our own
I disagree.
Future. In the physics of Christianity, you seem to reintroduce some version of a more traditional concept of a God who is external to the universe, as opposed to a God who has evolved within the universe. So it seems, maybe I just misunderstood your point, but it seems to me here that we have two different concepts of God, and I wonder how to put these two concepts together.
I think you've misunderstood what I meant by God in the physics of immortality. In both the physics of immortality and in the physics of Christianity, God has always been the cosmological singularity. The only difference is that in the physics of immortality, I was focused entirely on the final singularity to the neglect of the other two singularities which are out there. I used intelligent life only to show that in the very end of time, intelligent life would grow to infinity, which would justify saying that the final singularity is God. But I don't need to use that approach. In Physics of Christianity, and even more so in my third book, I will emphasize that the final singularity is, the three singularities together, which I call the cosmological singularity. They're only one singularity, although from our point of view, they appear as separate singularities. These singularities control the universe completely. And remember, the singularity is outside, at the edge of, you could say, of space and time. That is certainly the traditional picture of God. I would now describe the cosmological singularity in the following way. The cosmological singularity is an immaterial being which is transcendent to the universe, which exists necessarily, and which has brought the universe and indeed all of reality out of existence from nothing. Needless to say, that is about as traditional picture of God in the traditional sense that you can have.
I see, but this...
if you won't, I'll work through every single step of that.
This, how to say, mathematical concepts who controls the history of the universe still, and how to phrase that, is still not exactly what most believers mean when they think of God. They think of a personal God who loves them, who cares for them, who they can pray to. Where is this caring personal God aspect in your mathematical concept of cosmological singularity? Meantime, I see that Micah has joined us, so I will replace my video with Micah's, who hasn't appeared so far. Hello, Micah.
Hey, I just was thinking maybe another way to kind of take this question is that in the physics of immortality, there's the concept of the immanent presence of God versus the transcendent presence of God. And I think that a lot of the features that we're looking for to kind of fulfill our religious expectations of resurrection and experience and so forth occurs in the immanent presence of God, the living creatures leading up to the final singularity, rather than something that that is only accomplished at the final singularity, so to speak. So I think that seems to be a conceptual distinction, and maybe we could speak to that.
All right, let me answer this. Of course, I'm going to argue for theism, not deism. First of all, I describe in detail how this statement works in my physics of immortality. Namely, the singularity is not Hausdorff separated from any point of his creation. Now, what that means is that he, God, the singularity, although it's outside of space and time altogether, is nevertheless closer to you than your own skin. How that works mathematically, I'll let you go through the mathematics and see how that works. Now that shows you that God is really there. Now remember, he acts in the universe through the laws of physics. This is the traditional Christian view. Pannenberg and Physics of Christianity, I give the references, has established that this is the correct way to think of miracles. God always, in a miracle, works through the laws of physics. But that means, of course, that miracles actually exist. So he is acting on the universe here to let us know he is here. At the very start of this interview, I emphasize that if God, the singularity, controls everything, then it is not outside the realm of possibility that since we must do certain things that he wants us to do in order to accomplish his goal in the whole of creation in the far future, that he nudges us occasionally by giving us a message through prophets. Now, this is the picture which comes out from the burning bush. God is present there talking to Moses. Now, in this picture, what is really happening is that in the very beginning of time, before time began, the singularity, the cosmological singularity, adjusted the initial conditions in such a way that at the time, around 4,000 years ago, roughly, when Moses was on Mount Sinai, there was the air molecules moved in such a way, and the way they would move was controlled by the singularity at the beginning of time, moved in such a way that a message would come to Moses through the air into his ears. It could, of course, been a direct manipulation of his nerves. I can't distinguish between the two experimentally, but nevertheless, this was a real message from the singularity, from God to Moses. Now, you can follow through this with all the other messages which the religious have received over time. This shows you, computer died again, this shows you that the singularity is really there, acting in a way that we can see is extremely personal in human history. Now, all that I've said so far makes perfect sense physically, if you accept the idea, of course, that the universe is deterministic. That's why it's essential for theological purposes to drop this idea that the wave function is a probability amplitude. Once you have randomness in the universe, then you've destroyed determinism and you've destroyed this entire argument for God acting through the physical laws in a way that is completely understandable to physicists to actually give us messages. And looking at the whole of universal history, you can see that it is reasonable that these messages will actually occur. So that's why I find my picture of the physics and God being the singularity to bring, to be completely consistent with the feeling of which every religious person wants to have, that God really is talking to him. This makes perfect sense from the physics. Now that's, I think, what I have achieved. I've not been able to show that God really is talking to you, just that it makes perfect sense from the physics to think that occasionally he will talk to you. And you know how the Christian tradition asserts that God always wants to talk to you, that that's the purpose of prayer, is to open yourself to God's messages. You cannot in prayer tell God something that he does not already know. We are told in the Bible that he knew what you were going to do your whole entire life before you were born. He knew all this before creation began, before he began time, before he began the universe. But he's there, wanting to communicate with you, and all you have to do, this is traditional Christian theology, is open yourself up to him. I am saying that that's what the physics says. This makes perfect sense from the point of view of physics.
Thanks. Let's just move to the end of the prepared list. This is basically a part of what I was making before. In the physics of Christianity, described the physical mechanism of the resurrection of Jesus. Well, the wording that I'm using now is very imprecise, but my point was who, sense of an agency that we could conceive as a person in some sense, who affects the resurrection of Jesus. Or is it something that happens spontaneously in the universe? I guess the good answer could be both, but let's hear your answer.
There is no spontaneous action. Everything in reality is under the control of the singularity. Of course, the singularity resurrected Jesus. Now, in my scenario, which I describe in the physics of Christianity, that particular resurrection was a clear evidence of the activity of the singularity of God himself. Because in the mechanism I described, that would work only if neutrinos from every direction happen to appear in that particular area of Jerusalem in the precise sequence, and it would be let's see, something like 10 to the 30th power neutrinos, and these neutrinos would have to come from cosmological distances, from all directions in the cosmological distances to arrive on Earth at exactly the same time. This was planned in the beginning. of time that Jesus would resurrect at that time, if my scenario is correct, which is to say, it is obviously, if my scenario is correct, an act of God himself. It is a miracle of God in the sense of Tannenberg, in the traditional Christian sense. Now remember, the resurrection of Jesus is the justification for asserting that Jesus really is God. My particular proposed mechanism of how it works establishes that Jesus was God clearly and unequivocally.
Still, this concept of resurrection of Jesus is, as I see it, a very different one from the concept of our own resurrection at the end of time. The two things happen following a very different physical mechanism. Correct?
Correct.
That is correct. But I see no reason why God has to be restricted to one particular mechanism to achieve the same end.
Of course. I think I had one last point in my list, but I think you have commented on that already. You have said the same thing yourself about this that Pannenberg says in volume 2 of Systematic Theology. The divine reality, according to Tipler, does not come into being only at the Omega, but is to be thought of as free from all the restriction of time at the Omega. Therefore, in terms of the eschatological future, the divine reality is present at each phase of the cosmic process, and hence as already the creative origin of the universe at the beginning of its course. Now, Pannenberg
I agree totally.
Says a comment to your first book, not the last one, I guess. So he was describing a very preliminary version of your ideas. But I think in this discussion you have said something very similar yourself.
I'm sorry, I didn't catch that.
I think you have said something very similar yourself in this.
Yes. I agree with what Pannenberg says, and I think that's a very nice short description of the view I've been expounding today, and I've expounded in my books.
In this sense, the God which exists outside of space-time is the same God is active in the universe, anytime and everywhere.
Yes.
Okay, Micah, do you have some points?
Yeah, so one of the things that, going back to the discussion of the resurrection, one of the things that I think is interesting about the kind of resurrection proposal here is that it seems to be important that the resurrection the resurrection is important in large part because of the fact that it becomes known, because of the fact that it impacts history and changes the way we relate to history and so forth. And I think that's, in my reading, that's a very orthodox position. And it's at the same time one that a lot of kind of evangelical Christianity maybe downplays or misses the significance of, because we tend to take the crucifixion and resurrection of Jesus as if it did not happen in time, as if time wasn't significant. But in the Orthodox understanding, Jesus comes at exactly the right time to accomplish the purposes of God. And I find it interesting that this connects explicitly to that aspect of things.
I have nothing to add. I agree.
This has made me think a lot about just how we engage in sort of the anthropic principle, because the anthropic principle itself basically states that because we are improbable beings in a sense, or seemingly improbable, that we should actually look around and find ourselves in an improbable seeming reality as well. That many of the constants of physics and so forth have to be very specific values to attain that. And that's, in my estimation, another way of saying intelligent living beings are a miraculous thing, and we live in a miraculous universe in which we actually do expect to see a lot of miracles.
Miracles understood, of course, to be what they originally were. And Pannenberg, as I said, had a long paper on this, which I referenced in my book, The Physics of Christianity, that Christianity has always held that miracles are wonders. That's what it literally means, something we totally don't expect. But it does not mean that the laws of physics are suspended. Laws of physics are never suspended. God always works through the laws of physics, that he just uses it in a way that we are incapable of using. I mentioned the neutrinos over vast cosmological distances have to be perfectly aligned with each other in order for the resurrection of the Jesus to occur by my proposed mechanism. This shows you how totally in control God is of the universe, and how he is assuring that the universe will accomplish his purposes, which he set at the beginning of time. He is acting now. He has always acted, but always through the laws of physics, and it is always we see him in this very unlikely, from our point of view, way of appearing, namely that he organizes things over vast distances, so things just happen to come at the right time. But of course, he's already planned this before time began, that they will occur at just this time. This is a consequence of determinism coming from the singularity, and one of the points I make in a paper, which I'm going to put on the archive soon, namely that it is the singularity that gives rise. You could prove this mathematically remarkably using the theory of complex analysis, that the singularity creates not only...
I think we lost your voice again.
Let me try once again here. Can you hear me?
Yes, we can.
Yes, we can.
Okay. He creates not only the stuff in the universe, but you can see from complex analysis how the singularity creates the laws of physics themselves. Now, that's always been a problem for traditional science and theology analysis, because you don't understand how the laws of physics themselves can be created. But this shows you how God actually does this. And this reinforces the claim of St. Augustine that only God can be said to create. Because when we create something, we always act on what's there. We always act through the laws of physics. We cannot create the laws of physics. We always act on pre-existing matter. We never create the matter. The singularity creates the space-time. It creates the matter and energies in the space-time, and it creates the laws of physics which govern those things in space-time. This is what is remarkable that you can get out of the mathematics of modern physics.
So I had one question, and this requires speculation, so feel free to pass this up if you don't wish to engage in it. But kind of a niche theological question is what happened to Jesus after his ascension? So in the Christian account of things, Jesus is resurrected and walks around the earth for a short amount of time, and then ascends to heaven. And but we don't really know where that is or what that means exactly. And so where would you kind of locate that in this take on it?
Well, of course, I've thought about that. Remember what Acts tells us, that he goes up into the clouds that he is lost from view. Now, he disappears from the appearance of his disciples, and his appearance no longer being necessary. What I conjecture, and it's only that he just dissolved back into the neutrinos. That is, he no longer exists as a physical being in our space-time. He really continues to exist as he's always existed, as the all-present singularity. The singularity, in other words, which connects the beginning singularity, which I've identified with the Holy Spirit, in accordance with the first chapter of Genesis, and the final singularity, which I've identified with God the Father, in accordance with the third chapter of Exodus. All the presence of time correspond to I'll call it the second person singularity. He returns entirely to his deity. He then drops his immanence as a living being in our cosmos and returns entirely to a deity. But remember, in my physics of Christianity, I point out how he can return, and this is allowed because remember how the incarnation in my theory works, namely that there is a entanglement between Jesus the man living 2,000 years ago and the all-present singularity. They are entangled quantum mechanically, and once the Jesus the man is no longer required for God's purposes, he ceases to be in the sense of a man. He then returns entirely to his deity. He exists only as a singularity. But remember the orthodox position in Christianity. He does return, in a sense, as a man. In the miracle of transubstantiation in the Mass, in which the wine and the bread is transubstantiated into the body and blood of Jesus. What I am claiming is that indeed Jesus comes back as a quantum mechanical entanglement with the bread and the wine during the Mass. That is certainly once again allowed by the physics, so he is still here. He appears every Sunday in every Mass, which means all the time.
I think that was a great final point, and we have to thank Professor Frank Tipler for staying more than 2 hours with us, and that was a great discussion. And I think I will spend the next couple of weeks reading, trying to understand at least a little part of what you have explained.
Thank you for inviting me, gentlemen. I enjoyed it, and now I'm going to sign off.
Thank you very much for coming, and I hope to talk again soon.
I hope we can meet again in India.
I definitely hope so.